once every 3 years or so, we're able to give major awards to those members of our community that are particularly deserving of recognition. And this award session is the Martin J. Berger Award. For those of you who don't know, Martin Berger was a professor at MIT and University of Connecticut and wrote seminal textbooks in the field of crystallography. One of our real giants in the field. And the ACA has this award named after Martin Berger, and it's for exceptional distinction in any area of interest to the ACA. It says for mature scientists, but I thought that was kind of insulting, so I was debating whether to include that or not. But anyway, it's one of our more prestigious awards. Our Berger Award recipient is John Spence. John is a Regents Professor at Arizona State University. A Regents Professor is someone who transcends departmental boundaries and is recognized at his own university as being a scholar in the true sense of the word. His specialty has been in condensed matter physics, biophysics, and diffraction physics since his involvement in our society. He has studied in areas everywhere from basic physics, nanomaterials, and more recently, biophysics. His convergent beam methods have been critical for understanding bonding and dislocations, and more recently, he's turned his attention to femtosecond diffraction. This is a very exciting new area for crystallography and diffraction science. I'm predicting that these new sources, the free electron lasers, will do for structural science what synchrotrons did to revolutionize the field a few years ago. Along with the words come a framed plaque and an envelope with some extra spending money.
Thanks, George. This is a great honor, and I'm very grateful. It's often said that our field is a mature field. What I want to suggest today is that that's not correct, and that in fact there's a lot of diffraction physics yet to be done in crystallography if we extend the term to include time-dependent analysis and nanocrystals and many other things, which I'll talk about. But before I start on that, let me say something briefly about Berger and his life's work, which in many ways paralleled that of Bragg. In fact, it was inspired by a talk which Bragg the Younger gave in MIT in 1927. He was famous for his exhaustive thoroughness. He wrote 27 books, 12 textbooks, I'm sorry, and many papers tackling the great problems of the day in crystallography: extinction, polymorphism, twinning, and counter diffraction. And there's a mineral named for him. He was, of course, the inventor of the precession camera. I came across his work when John Cowley, who was my mentor, gave me his book, Vector Spaces, a long time ago. Now, John had been at MIT as a postdoc in the early 50s with both Warren and Berger. It's interesting that Berger's work sort of paralleled that of Bragg in the sense that both of them in the 20s and 30s solved lots of mineral structures and soap in addition. And remember, this is in the days where there were no computers. Now, it's incredibly difficult for young people to imagine what it's like to solve a crystal structure without a computer. But it could be done. They used clever symmetry arguments. And in particular, in 1929, Bragg suggested doing optical reconstructions. Berger's version of that was much better and cleverer. He used polarizers to introduce phasers in his optical reconstruction. And instead of a brass plate with holes drilled in it, whose size were proportional to the structure factors, illuminated by coherent light, and remember there were no lasers in those days, Berger used polarizers across the holes. He also pointed out that if you made the holes bigger, proportional to the square of the structure factor, you could get a Patterson map. Now, his Vector Spaces book is really a fascinating and very clever book. It's a method of solving these Patterson functions by what he called his image-seeking method. He used a positive X-ray film as a mask in the backfocal plane of a lens to get essentially a photograph of the atoms in the crystal. to get real-time sort of speed of light Fourier transform. He was also fascinated by the question of whether crystallography is unique. Can you have two different crystals with the same diffraction pattern? The answer is yes, as famously demonstrated by Pauling in the 30s with his Bixbyite, a mineral which came from a town in Arizona not far from where I live. So what was pointed out by several scientists was that if you take a lattice and convolve it with a motif, you get a certain diffraction pattern. If you convolve it with the inverse of that motif, you get a different crystal structure but the same diffraction pattern. And notice that the two resulting structures are not enantiomorphs. So here was a clear evidence that you could come up with more than one structure to give the same diffraction pattern. We came across a similar thing in some work in about 2003 at the ALS, where we were trying to do lensless imaging. And I should say that in the last 10 years, I've really seen two important breakthroughs. The first has been the development of lensless imaging with X-ray diffraction, and the second is this idea that with sufficiently brief pulses, you can outrun radiation damage. All that's happened since about 2000. The lensless imaging asks us to solve the phase problem for samples which are not periodic. And here, in some work of ours at the ALS around 2004, we made a sample consisting of gold balls, which are shown here. So this is a TEM image, or an SEM image, showing the gold balls. The Patterson functions, which Berger spent so much of his time devoted to, are maps of all interatomic vectors. So here are some interatomic vectors. Above is shown a soft X-ray diffraction pattern from these gold balls. It's the Patterson map. And as you could think of this as an example of an application of Berger's image-seeking method, because if you have, or of the heavy atom method indeed, if you have an isolated ball, such as the one here at A, it tends to form images of other clusters because the Patterson is simply the convolution of all pairs of these with a change of sign. So if I look up here, you can see three balls sitting close together in the Patterson map. And they're a faithful image of the three balls in the actual real space sample or structure. So these three balls are imaged in this ball at the origin to produce this cluster of three, a faithful image, in the Patterson map. And I think Berger would have been fascinated to see how that can be done with objects now which are not periodic. That led on to this work with Stefano Marchesini, led this effort a bit later at the ALS, where we were able to develop what's become known as the Shrinkwrap algorithm, in which by iterative methods we can phase these patterns. But Stefano had the excellent idea of thresholding during the iterations. What's important when you're phasing like this is the boundary of the object, what mathematicians call the support. And Stefano had the idea that in each iteration of a method rather like solvent flattening, you make a new and improved estimate of the boundary of the object. And that's why we called it Shrinkwrap. So if I run this movie, now, this is the Patterson, the autocorrelation, just the Fourier transform of the diffraction intensities from a non-periodic object taken at the ALS with soft X-rays in transmission. And what you'll see as the movie runs is the Patterson turn into the real space image as the boundary is, the estimate of boundary is improved with the iterations. So here it runs now, and you can see it's chosen one side. Of course, Pattersons have inversion symmetry, and it's selected this side. It's constantly thresholding the boundary, and the algorithm, which is like solvent flattening, running between real and reciprocal space, putting in imposing known information in each step, slowly improves its estimate and changes it from an autocorrelation function to a real space image of the gold balls. And now it's converged, and we find that this is a nice picture of the balls that 50 nanometer gold balls that we can see with an SEM. Well, that led on in this work with Antoine Barty and Henry Chapman in 2006 to real three-dimensional images by tomography of non-periodic samples. So this is an image of these gold balls decorating a pyramid reconstructed from soft X-ray transmission diffraction patterns. And since then, this field has really blossomed, and many people around the world now are improving on this. I think the latest developments would be the typography work of Pierre Thibault and others. John Rodenberg, of course, has been a key figure. But we're seeing more and more of this lensless X-ray imaging of non-periodic objects. It's been extended to electron diffraction in this work by Jianmin Zhuo from Illinois. And this is the first and only image at atomic resolution by lensless imaging, where you reconstruct the image from the diffraction pattern alone without using a lens. And he's attained atomic resolution for this image of a carbon nanotube. Here's a structural model of it. So he put one nanotube across a hole in the TEM and got an electron diffraction pattern from that one nanotube with a beam diameter of a few nanometers. It's fully coherent because it's a field emission gun. And by the iterative phasing methods I've been talking about, mainly developed by Jim Feenup, Gershberg and Saxon and others, he was able to reconstruct an atomic resolution image. In our own lab, again working with Jianmin Zhuo when he was my postdoc and graduate student, we devoted about 10 years to trying to make electron diffraction a quantitative method. And this was following some work, early work by the Australian group, Alec Moody and others, Peter Goodman, and Gunter Lenfel, where they'd shown that you can record these convergent beam diffraction patterns where, by using a cone of illumination, the Bragg spots open up into disks. And it's the intensity within the disks that we measure and analyze. And here's a comparison of the theory and experiment. And you have to understand how bad the agreement between theory and experiment was in electron microscopy to appreciate this achievement of Zhuo's. I mean, for many years, electron microscopy has been thought of as a way of getting pretty pictures of things which help eliminate models for defects and so forth. But to get quantitative agreement is really an achievement, and that was possible by some advances in technology, the elastic energy filter, the use of image plates, but above all by accurate multiple scattering calculations. So because our probe now is smaller than one mosaic block, we can get very accurate data using the perfect crystal theory. So this is multiple elastic scattering calculations compared with experiment, and you see it fits very well. It fits so well that you can start to refine bonding effects. And this was the main work we did with Mike O'Keefe, who was a powerful force in all this kind of thing, for cuprite. Now, this is a difference map, and the reference atoms are ions. So if cuprite were ionic, this picture would be blank. What you're seeing here is the difference between the total density and the ions. And as Mike kept pointing out, it was wonderful to work with him because he's so knowledgeable on these things. The amount of charge redistribution, which accounts for the formation of all the matter in the universe when atoms come together, is fantastically small. It's less than 0.03% of all the valence electron distribution. That is to say, if you bring neutral atoms together and put them on lattice sites, gas phase atoms, they already overlap. And that neutral atom overlap is most of the bond. The additional readjustment, which accounts for the reduction in energy that makes our world the way it is in chemistry, is tiny. And we could see it here, and in fact, Zhuo's refinement was accurate enough to measure the amount of charge in the bond. So because we're using multiple scattering calculations, we have no extinction errors. And you could say that this is an extinction-free refinement. The other last point I'd make about electron diffraction is that the interaction is so strong that it's very good for the study of diffuse scattering. So here's magnetite, which famously has a Verbe metal insulated transition about 120 K. As you go through the transition, the patterns light up with all this diffuse scattering. And of course, with the LCLS, we could get similar results now, but that wasn't possible. And I think the interaction is still stronger than the synchrotron here, but it's really a good way to study diffuse scattering at phase transitions. And by modeling that, we could come up with a model for the polaron ordering, which accounts for the Verbe transition in magnetite at 120 K. The final thing I would mention here in this sort of miscellaneous introduction of topics is some work on powder diffraction, where we were really astonished by the power and success of this flipping method that came out in 2003. Oslani and Tsuto were the authors of that paper in Active Crystal. And it was an extraordinary thing because it's such a simple algorithm for solving the phase problem. You immediately thought that if someone had thought of this in 1965, the whole history of crystallography would have been completely different. We wouldn't have needed direct methods or MAD or SAD, or, well, of course, I guess we would have, but certainly people would have had, for small molecules, for 40 years, a method which solved the phase problem for them fairly straightforwardly. The method is iterative, and in real space, you just reverse the sign of all the density less than a certain threshold and impose the known structure factors, the measured structure factor moduli in real space and iterate, and it converges wonderfully, and there's been a flood of publications on that. So with Mike, again, I asked my student Wu to look into this, and we developed a method of merging that in powder diffraction using basically the Lebel method. But in Lebel, so here's our algorithm. It's iterative, it's based on the flipping algorithm. Our newest, so just to remind you, in powder diffraction, you'd like to have a situation where each ring is one structure factor. Because of limited angular resolution, that's never true, but remember that for low symmetry space groups, at least formally, every ring is a different structure factor. For crystal with symmetry lower than orthorhombic, I think. So as Bob Vondriel has proven over the years, if we can get the instrumental angular resolution better, there's hope to do things by this far more efficient method. And our algorithm just says that our new estimate, it combines the flipping and phasing algorithm in one step with this Lebel step where you unravel the overlaps, where two different structure factors may contribute to the same ring. So our new estimate of a structure factor is given by the previous estimate times a certain ratio. That ratio is the experimental ring intensity divided by the current estimate of the ring intensity. And we find that this converges, and we're able to solve a number of new structures that way. For example, here in pyrite, FeS2, here's an example of this cubic structure where, of course, these two reflections have different structure factors, but at the same scattering angle, and yet they are resolved with differing structure factors by the algorithm. And there are a number of papers on that in which we've solved new structures. It's turned out to be very useful in catalysis. A problem that I've worked on all my life, really, and not got very far with at all, is the removal of multiple scattering artifacts, both from electron and soft X-ray diffraction, where it's a very important problem. Here are some of the approaches, and just let me say, the only one that really has worked out to work after 40 years of work is this two-wavelength method for soft X-rays. It turns out that the scattering of soft X-rays is proportional both to the wavelength and to the thickness of the sample, so that if you take patterns of two different wavelengths, which is easy to do on a synchrotron, and divide one by the other, then you can extract the single scattering from the multiple scattering. I'll spend the rest of the time on our recent work now at SLAC. So we've been at this for about 2 years now. So I thought the best thing to do is just give you a kind of status report and mention the highlights that have, the milestones that have been achieved over those 2 years. It's completely exhausting. These people who are constantly jet lagged, sleeping on the floor, eating bad food in a cave for a week, and of course, because we developed the data analysis method, the nanocrystals, and also the sample delivery device, we tend to be involved in every project where people want to solve crystals or crystallites at the LCLS. So it has been a very heavy involvement from my group for 2 years, and we're all exhausted. So this machine, here it is, it's over 100 meters long. It produces pulses of X-rays, now runs up to 9 kV, with about 10 to the 12 photons per pulse. And you get about 100 of those patterns per second. So the detector is reading out 100 diffraction patterns a second. You get mountains of data, and the pulse duration is about 70 femtosecond. Now the divide period is perhaps 100 femtosecond. So each snapshot is briefer than it takes for the nucleus to vibrate once. But it's not as short as the period for an electron to orbit an atom. Here's our experimental geometry. This is the sample injection device. The pulses are so intense that they destroy the sample. But the main finding has been that if your pulse is brief enough, you get the diffraction pattern before the sample is destroyed. That is, the pulses terminate before the photoelectron avalanche or cascade develops. In that way, you can see that if you can pack enough photons into this pulse and make it short enough, you separate out the effects of radiation dose and damage and sample size and resolution. Because as we all know in protein crystallography, the quality of our data is limited by two things: the quality of the sample and radiation damage. Now, if you can pack an infinite number of photons into a delta function at an instant of time, you get the instantaneous elastic scattering from a sample of any size, from one molecule if you like. It's just a matter of how many photons you can pack into the pulse. That is the main point of my talk. Yeah? There have been many papers, Bob Glaser for example, calculating how many molecules are needed in a crystal to provide a given resolution for a given dose. Because of course the fine detail in diffraction patterns is destroyed first. If we can put all our photons in a sufficiently brief pulse, it doesn't matter how big the sample is or what the dose is, because we get the instantaneous elastic scattering first. I say instantaneous, but of course the rate at which you get the Thomson scattering is proportional to the rate at which photons are arriving. So just let me repeat that, because it really is the main point. I said I've seen two discoveries in the last 10 years. Lensless diffractive imaging and, well, what we're going to call serial femtosecond crystallography. The quality of data is limited by damage and crystal quality. We use the LCLS to get good time resolution. I'm sorry. We use the LCLS pulses not to get good time resolution, but to outrun damage. Yeah? And the protein nanocrystals may be more perfect than large crystals, and the evidence here is due to Bob von Driel, who is sitting here and writing papers on that. His powder protein diffraction work has shown that at room temperature. So this serial femtosecond crystallography breaks the nexus between crystal size, resolution, and dose. But you have to remember that you need a constant supply of crystals if you're going to do this, 100 crystals per second. So we use nanocrystals in a jet, and a constantly refreshed supply, but of course there's no goniometer. So we needed to develop a method of analyzing data from nanocrystals in random orientations. That was the PhD work of my student Rick Kirian, and we published two papers on that, and basically we did the only thing you can do, which is to assume that by chance there will be a nanocrystal in every possible orientation after recording 100 patterns per second for 16 hours or so, and that these will sample all the points sufficiently across the rocking curve to give you the angular integration you need to merge those partial reflections into full reflections. And we're aware of the work on that. So how to deliver the particles? Here's the injection device. We started work on this in about 2004 in my lab at the ALS. I made the first one of these. It didn't work too well. We tested at the ALS. Uwe Weierstahl made the one we used in December of '09 to get the first results from Petra Fromm's samples. And finally, Bruce Doak now has become seriously interested in this and made the kind of Rolls-Royce version, which really works beautiful, and it's a sophisticated scientific instrument. The problem was that the jets kept clogging. So back in 1890, Rayleigh showed in a beautiful paper that a column of liquid breaks up into droplets. This is called a Rayleigh instability by a necking instability. You see this here. You can drive these jets with a piezo. It's a bit like an inkjet printer, and this would run at perhaps 100 megahertz. Now we can put our X-ray beam here. We put our viruses, single particles, or nanocrystals, protein nanocrystals in the liquid here. So you're now, instead of mounting a crystal on a goniometer, you're working from HPLC and a liquid supply system. Quite a different way of working. And the other point about the short pulses defeating the damage problem is that you can work at room temperature. And the fact that we can work at room temperature in liquid phase opens the way to doing room temperature dynamics. Snapshot, room temperature, chemical dynamics. That's where we're headed with this work. So the samples come in this liquid stream, but clogging was a big problem, and Bruce it was who suggested that we could focus the liquid with the gas. So the way we made these, and Dan DuPont was a key figure in this, send the liquid with the proteins in it down the center of that, and mount that coaxially inside a capillary tube. The glass has been melted over at the end here with a hydrogen flame, and we have high pressure helium gas in here. Now the liquid coming out the end here is entrained in the gas, and because we speed up the liquid, it thins out. Remember, area times velocity is constant for incompressible fluid flow. So where I'm pointing now is actually liquid, not glass, and that makes a cone, a bit like the Taylor cone in the electrospray, and that produces a line of droplets out here. Rayleigh's original paper is quite wonderful. He used a spark gap as a flash to get flash photography. This is 1890. And he used a tuning fork to drive this droplet beam. And you can do this yourself if you turn the tap on slightly or force it and get it dripping, and then hold the cell phone up to it, making a single tone. You'll see that the droplet stream synchronizes with the cell phone. But his pictures are almost as good as ours back in 1890, using electrical spark to do flash photography. And of course you can synchronize all this and get stroboscopic images, and we have lots of papers on all of that kind of thing. Here's Bruce Doak's final implementation of the injector, version 3, and it's large and complicated. The main thing we did was to add a camera above, which is looking down through a prism. Here are the X-rays coming in, scattered out, and here is our pump laser, which we added to, so we could do pump probe work in the jet. Now that's very preliminary work, and it's too soon to say whether this is really going to be useful, but it's certainly worth trying. So here's the patterns as they come in the control room. Bill Mashnikin, this is lysozyme. I said we get 100 patterns a second. Well, this is what it looks like if you see them just coming in. And of course, since they're crystallites, little submicron or micron-sized crystallites of lysozyme, 100 snapshots a second being displayed. That's exactly like powder diffraction. Powder diffraction is the sum of diffraction from microcrystals lying in random orientations. Time-resolved crystallography, serial crystallography, the LCLS, is also the sum you're seeing here of diffraction from randomly oriented crystallites. So we get rings, and we can tell when we have enough data, when the signal to noise at the edge of the detector is good enough to stop collecting data and let the next person on. Now, I mentioned the problems with the shape transforms. These crystallites are so small that you get significant shape transform effects. That is to say, the Fourier transform of the external shape of the crystal is laid down around each lattice side. We assume that our crystals are smaller than one mosaic block, as in the electron diffraction case. So it's not mosaicity that's the problem, it's just the shape transform. If it's a cube of crystal, then we'd see a sinc function here. And our momentum and energy conserving evolved sphere will cut through somewhere in the subsidiary minima of the shape transform, which might be here. Well, then you'll get intensity in this direction, which is not the Bragg direction. The Bragg law is satisfied for rays passing, as it were, through a lattice point. That complicates the indexing tremendously. You have to ask whether, of course, with a million diffraction patterns, you have to develop automated indexing. And we use Moths film in our lab, but it has trouble if the spots are not in Bragg condition, which they won't be if the crystal is too small. Most of these crystals are about a micron. I should have said everything's about a micron here. The X-ray beam diameter is about a micron. The droplets are about a micron. The crystallites are about a micron. So in Bruce Doak's design, you need the X-ray beam and the droplet beam and the optic axis of the microscope and the axis of the lens focusing the pump laser in, all to pass through a common interaction volume of about a micron cubed. Now that's very challenging design, and we have precision motions there, and a lot of the effort over the last year has been to get that working and that precision that we need. So what have we achieved so far? The first question was, can this diffract and destroy method, where you get the pattern before you blow up the sample, can it give us atomic resolution? And that was a real question. We really didn't know. Nobody knew. All we had was Henry's paper from 2006, who'd shown that at very low resolution, sort of micron resolution, you could get some sort of pattern before the sample was destroyed. But that was not for a crystal. And there were many skeptics. So we were really thrilled in the middle of last year when we got this pattern at 3 angstrom resolution from Photosystem 1 at 9 kV. And since then, we've done much better. We in fact have, just last week, our paper came out in Science where we have 1.8 angstrom resolution from lysosine. So the resolution is currently 1.8 angstroms. This is Photosystem 1, and it's not a bad pattern by the standards of conventional crystallography. In lysozyme, as I mentioned, the latest work, this is led by Buerger and Ilva Schlichting's lab in Heidelberg, made the samples injected with our jet, analyzed by this Monte Carlo method. Now, the gray here are guides for the eye. These are the meshes for 2 sequences, one for turkey and one for hen. And it was remarkable for me, with not being a biologist, to see that just by looking, to have sufficient resolution, 1.8 angstroms, or 1.9 maybe, to distinguish the amino acid sequences from a hen from that of a turkey. The R factors of that, I have a table of R factors. We did a very extensive comparison of the LCLS results with results from similar samples at other synchrotrons. That's all in our paper. The second milestone is, can diffract and destroy produce any new biology? Well, I think that's still not quite decided, but certainly there's beautiful work from Deci, this is Koopman and others, using our injector and data analysis method, who have grown crystals inside a cell. So this is in vitro, and they're looking at a drug target for sleeping sickness. It's an enzyme called catepsin. It was made by the usual recombinant DNA being injected by a virus into a cell, and that was overexpressed protein we were interested in. We could see from this TEM image that was producing crystals from the facets here. We then extracted the crystals from the cells, put them in our liquid jet, and got thousands of diffraction patterns. Well, the quality of the patterns was very good. And here's an example of merged data from that. But look how inefficient the process is at the moment, and I'll say something about how we can improve this in a minute. We collected 4 million frame diffraction patterns over 8 hours, of which only 350,000 were hits. Often the beam doesn't hit a crystal. You can, of course, synchronize the droplets with the beam. We haven't done that yet, but obviously with the piezo driver, this could all be synchronized. And there's another mode called droplet on demand to consider. But of those 350,000 hits, only 150,000 could be indexed, 44%. So it's extremely inefficient. But we extracted the good data, and with lots of data analysis, came up with this density map. And again, for me as a non-biologist, I was fascinated to see this post-translational modification, the glycosylation, where this is new structure which hadn't been seen before. This carbohydrate sugar string has been attached to the protein after the protein is formed in the ribosome. So, and it sticks on at the 216th residue. So it's nicely resolved in this map, and actually this is a low resolution, 3.5 angstroms. There are better maps but better than 2 angstroms. So this is thought to help with rational drug design, but I have to say that whether one can say anything about binding affinities of drug molecules onto this protein from our map is yet to be decided. So the paper's finished, but we're still arguing about what we can say about targeting of small molecules onto this, the ligand. And here is the new structure which we saw here. It's the propeptide. This is this stuff is the old structure which was known. There's the catepsin, which occurs, enzyme in the insect, which bites you, gets in your bloodstream, goes to your head, and I think it attacks the white blood cells and gives you sleeping sickness. This affects about 50 million people. And then there's human catepsin. These have to be distinguished. So this is the previously known structure here. This is the new thing that we saw, plus that sugar that I showed attached to 216. The next milestone, I think, over the last 2 years has been our effort at time-resolved work. Now, this is yet to be proven, but it was worth a try. And let me show you how far we've got. So here, we bring in a pump laser slightly upstream of the X-ray beam, taking the snapshots. So, and we're working on photosystem 1 and 2. So we have this optical trigger that you need. We excite the molecules slightly before they run down into the X-ray beam here, and then take their snapshot. And the time delay here is 30 microns. So remember, the X-ray pulses are 70 femtoseconds, and we're taking different frames of a movie with a delay between when we excite the molecule in a nanocrystal and when we take the snapshot of about 30 microseconds. Now, I was saying that the precision of the optical axis alignment here is critical. So this is a view looking along the jet. And the X-ray beam comes in there. The detector's over here. Here's the optical microscope, so you can see what's going on from the control room. There's a prism here. We're looking down here into an LED. And finally, here's our pump laser, which is exciting the molecules, sort of as it were, behind the screen there. Behind the screen, prior to their arrival at the X-ray beam. So here's photosystem 1, I'm sorry, that we've been studying. All this is made in Petra Fromm's lab. She's an expert on photosystem. It's a megadalton, so it's a huge molecule with 72,000 atoms. And there is an auxiliary molecule called ferredoxin, which plays a role in photosynthesis. When a photon comes in at the top from the sun, this is like sunlight falling on a leaf. There's an antenna complex at the top which collects the photons. They're passed down through the photosystem molecule by a series of redox reactions with the ultimate effect of undocking a molecule. It doesn't jump backwards and forwards like this, it undocks from here. And our aim was to see that process with this snapshot technique in the jet. Well, here's what it looks like on the screen. And this is real time, seen through that camera in vacuum. And you see here the X-ray beam coming along here. It's blowing up the little nanocrystals of photosystem 1 with ferredoxin attached. And here's the pump laser slightly upstream, which is exciting them before they travel on to have their snapshot taken here. This thing here is just ice that's grown down from above, and that will eventually break off. And we found that we could get rid of it by illuminating with the pump laser, moving things around. So that's how it looks in the control room. The delay then was, I think, 30 microseconds. And of course, you have to get lots of shots for each delay to make one three-dimensional reconstruction, right? So all the patterns have to be indexed in order to merge them for a particular delay. Then we change the delay and repeat all that for a different delay, which gives us another frame. It's just following in the steps of Keith Moffat and other people who've worked, Anfred Rood, and also Richard Neutzer is with us on this work, much more experienced than me and have done, I think, the time-resolved crystallography in the past. So here's our result, which is now published. It's Andy Aquila is the lead author. We did get a difference between the ground state. This is a difference. The structure factors is a function of scattering angle for 3 delays, 0 delay, 5 microseconds, and 10 microseconds. And you see that the changes in the structure factor exceed the noise. But I wouldn't want to say much more than that from this first attempt, because this is all very low resolution. This is 10 angstrom resolution out here. And of course, the important changes you're after are really off the scale here. As James has pointed out, this low angle scattering will be mostly related to the water. But there is a difference, and we want to continue with this and see if we can, we have another time to try and extend this to higher resolution. An obvious thing to do is to look at the damage as a function of the pulse duration. If the pulses are long enough, then the photons arriving at the end of the pulse will be diffracting from already damaged crystal. So if we make our pulse sufficiently long, we should get bad diffraction patterns. In particular, there should be spot fading. The high order should fade first. as has been shown in many studies, including those by James Holden. So here are the results on that, showing scattering from photosystem 1 as a function of angle for 3 different pulse durations. And you see that as you go out to 200 femtosecond pulses, sure enough, the pulses fall, the intensity falls off more rapidly. But it was, I mean, we really had no idea what pulse duration was going to work. There was theory. The theory was being done by people at Livermore, Stefan Hauriga, Carl Kalman, and others. But really, you needed parameters from the experiment to make the theory work. And I should say that some of those theory calculations were based on the code that's used to model nuclear explosions at Livermore. It was the Livermore atom bomb group who did these some of these calculations. And what we found surprised us. You can imagine that at 10 femtoseconds you might not expect any damage. But in fact, at this resolution, we found that we could go out to 70 femtoseconds without much loss of quality in the diffraction patterns. So we've tended to stick with pulses of about 50. That's the magic number. 50 femtoseconds is what you need to avoid damage, loosely speaking. Of course, it is a function of resolution. Okay, I'll finish up with just saying where we're headed now with new things that we haven't fully tried that might or might not work. Now, a striking thing about the early patterns was that from the smallest crystals, we got all this scattering between the Bragg reflections, as you might expect. If you just think about a one-dimensional grating of n slits, it has n-2 subsidiary minima between the major Bragg spots. And sure enough, we see them here. Well, that means that if you count these fringes and add 2, it tells you the number of unit cells in the nanocrystal between facets along this direction. So we can tell the size of the crystal. This bright red streak is the scattering from the jet itself. This is diffraction from a tube of liquid. But of course, as Perutz in the 50s and David Sayer and others have pointed out, if you have scattering between Bragg reflections, this is like a non-crystallographic symmetry, I guess, you can solve the phase problem, or it's a big help. And so that's another aspect that we're working on now, and we have a beam time in a few months, where I'll be working with my postdoc, Nadia, to try that. We want to see if we can develop a method for low resolution phasing, direct digital phasing at low resolution, from using nanocrystals. That would be good because you know messy chemicals, you don't have to make chemical modifications to the sample, as in MAD or SAD. So that's one direction we're headed in. Henry Chapman and Robin Santra have developed a theory of MAD for femtosecond crystallography. Now, the problem you then have is you sort of time-dependent absorption coefficients. And Robin has worked out the rate equations for the transitions occurring in all the atoms as the pulse progresses in time. And I guess he'll publish, there'll be new tables of absorption coefficients to use in MAD with short pulses. That's what will come out of that. But the nanocrystal method that we're pursuing just depends on the fact that you have these shape transforms and therefore scattering between the Bragg reflections, which allows you to satisfy Shannon's theorem rather than Bragg's law, and gives us the information we need for these iterative phasing algorithms to converge. Now, I showed how inefficient the process was. Uwe Weierstahl has really been the leader in trying to do something about that. And we're working with Ray Stevens here on these GPCRs, which I believe are drug targets for 60% of drugs. And the point about them is that they're membrane proteins, and they like to live in lipid cubic phase. So Uwe had the idea of trying to run our jet with lipid cubic phase instead of just buffer solution. Well, of course, lipid cubic phase is much more viscous, so the jet runs much more slowly. That's good. If you can see that if you match the rep rate of the laser with the velocity of the particles, you could hope to hit every particle. Now, the velocity of the jet depends on many things, the pressure, but also the viscosity. And our buffer-based jet, liquid jet, runs much too fast. It's about 10 microns per microsecond. So we think of this as a kind of toothpaste jet now, yeah, with LCP, and lots of membrane proteins love to live in that stuff, and so they come out rather slowly, and therefore we can hope to hit most of them and get the hit rate up. Well, here's a movie, and I can see now, if you look here, there's a bright dot moving along, Here's another one. That's an actual crystal. And this bulge here is where the LCLS is hitting the crystals. That's where they're exploding. We have to worry about debris, running along the jet, which may interfere with other crystals, or I don't know about that. But you can see that the crystals are moving along. This is real time, and this is taken at the LCLS. So you can see how slowly they're moving. The jet remains straight. It's in vacuum, so it will freeze up here. And we had a big problem with the phase transition in LCP. We're working with Martin Caffrey here in Ireland, and in our first experiments, as the LCP material comes out here, it freezes, and you get very sharp spots from the low temperature phase of LCP, so powerful that they damage the detector. Ice is a big problem too, as you know from PX, MX. If you get ice crystals, you can get extremely intense spots which will damage your detector. So that was a problem, and Martin then very cleverly made us he's a master of the chemistry of these things, made a new phase which doesn't freeze in vacuum or freezes at a much lower temperature. And we now have an LCP phase which runs without producing these spots. And I think we can get, that means much higher hit rate, perhaps 80% or so. And that's really important because it means we can use far less protein. You see, the Photosystem 1, the reason I went to Petra Fromm to ask her to try and provide some samples for us back in 2005 was that we needed something of which you could make huge quantities because we knew it was going to be very inefficient. I also wanted something I thought was fundable. I had great trouble getting funding for this work. And in Photosystem 1, it sort of sounds like energy and DOE, so we thought we'd get money out of DOE. And of course, membrane proteins are famously difficult to crystallize. And if you believe, like Bob von Driel, that there are lots of proteins which make little crystals but won't grow to big ones, then this is also worth doing. So that's the toothpaste jet, and it does promise to allow us to use much smaller quantities of protein. We needed buckets of protein for the Photosystem 1. Here, traveling at perhaps 100 times slower speed, we only need tiny amounts of protein to do this. And one could therefore think of tackling human protein. It says here that a carat weight of protein crystal is 12,000 times more expensive than a carat of diamond. Another project in my lab with Dinji Wang, a student, he's made a mixing jet. So we want to do mixing experiments. Now, people have done this before with synchrotrons, of course, Louise Pollock at Cornell, amongst others. But we found a company that makes fiber optic that has 2 holes in the fiber optic, not one. So we can bring an enzyme down one hole and substrate down the other and let them mix at the nozzle. So we have a high pressure gas here focusing this. So this is running now, and the 2 solutions are mixing here. It's coming out into vacuum. It'll freeze up here. There'll be little ice balls here, nano ice droplets, spherical. And we can bring our X-ray beam across here at any point we like. So we have temperature variation along here, which will please Peter greatly. And we have chemistry occurring as the enzyme is taken through its cycle by its reaction with the substrate at that point. And we have an experiment there, I should say, that Seb Doniak's involved in that in a few months. Now, I'll end up with just some comments on snapshot SACs. What happens if you do SACs with short pulses? Well, what happens was pointed out, or suggested first, in some remarkable papers by Zvi Kam in 1978. He said the following thing: SACs data is one-dimensional. It's isotropic around a ring. If you take a snapshot where the exposure time is briefer than the rotational diffusion time of the molecules, so the molecule does not rotate during the exposure, then a SACs pattern, solution scattering, becomes two-dimensional, not one-dimensional. Now, this two-dimensionality is not due, the part we're interested in, is not due to interference between rays scattered from different molecules. That's a coherent interference effect, intermolecule scattering, that we're not interested in. Even if you eliminate that type of scattering, you get patterns which are two-dimensional. Now, in SACs, we're trying to reconstruct a three-dimensional model from the one-dimensional SACs pattern And you can see that you've got a much better chance of doing that if you start with a two-dimensional pattern. There's more information in a two-dimensional pattern to get you to 3 dimensions than from 1 dimension. That was Cam's original point. And I should say that Delano Salden, who's here, has had some wonderful ideas about that and has published a series of papers which, if you're interested in this, you should definitely read, particularly for the problem of reconstructing icosahedral viruses. He has a method there that will work, and others have worked on it as well. So the question then is how to extract an image of one particle using a scattering from many copies. Do that, and we'd like to do that ab initio without Sachs modeling, and Cam, as I said, was the first to suggest how this might be done. And his method is ab initio. It is not modeling the way you do it in Sachs. This is ab initio. You go directly from the 2D snapshot Sachs pattern to the structure without modeling. Well, we have preliminary results. Here's just a simulation from Delano showing what these 2D snapshot Sachs patterns, snapshot solution scattering patterns look like. They have these fluctuations around here. And we work in terms of the angular correlation function. That is to say, in simplest terms, it's the intensity around a ring convolved with itself for different displacements in angle. And in this work, which we did at the ALS, instead of having particles frozen in time, as you would at the LCLS, they were frozen in space. So Cam's ideas work for particles frozen in either time or space. And here's basically the key idea of his theory. This is a TEM image of some gold rods lying on their side. So in this experiment, we reduced everything to just 2 dimensions. The 3-dimensional theory goes through similarly, but it's much more complicated. So we have gold rods lying on their side. Let's say they're identical, and they differ only by rotation normal to this silicon nitride membrane. From one of those, we can get a diffraction pattern in transmission, and from that, we can decompose it into rings and form the angular correlation pattern around every ring. Now we can repeat that with a different group of statistically equivalent rods and get another angular correlation function. What Cam's paper shows is that if you sum enough of these, they converge to the angular correlation function of one particle. Now this is a truly remarkable result. I mean, he has disentangled orientational disorder by this method. Whether it's practical in 3D is a question. The computing resources you need are enormous. So having got the angular correlation of one particle, you'd like to get back to a charge density map of a typical particle, but that can be done, and Delano has a way to do it using triple correlations. It can also be done, loosely speaking, by phasing twice. The first phasing effort would take us from the angular autocorrelation of one particle to the diffraction pattern. This is like it's a bit like a Patterson. And if we go then phase that, we can get from that to the image. This is the autocorrelation of the image. So if we phase twice, we can go from the angular autocorrelation of one particle back to a real space image. And in this paper in PRL, led by Delano a couple of years ago, with David Shapiro and others at the ALS, we indeed started with these gold rods lying on their side and reconstructed this image of a gold rod. But what was interesting is that it had a dot in the middle of it. Now, we bought a bottle of gold nanorods, little dots in it as well. And you can see here a gold dot. And sure enough, in the reconstruction, we get a dot on top of a rod. It's an interesting question as to why the dot is where it is. Why does it put the dot in the middle of the rod? I mean, maybe this has to do with the choice of starting phases in the iterative algorithm or something. But it does show that the inversion process is linear, and you can deal with mixtures, which would be important if we're looking at proteins with different conformations in solution. Now, extending this to proteins is a huge step, and it may not be possible, but Haifang Liu and Peter, working with Peter Svart and Delano, we have now extended this to particles of iron oxide. Extending it to proteins is very difficult because the contrast, of course, between the protein and the buffer solution is so small. And life is made a lot easier when you have inorganic particles with much stronger scattering. But here they are. We call them nanorice. and they're lying on their side. And this is now is an attempt to do the three-dimensional reconstruction by a slightly different method, which does involve modeling. And we get these three reconstructions here of these particles. They're obviously not all identical, so this is some kind of average. And Haifeng Liu has now done simulations also for proteins. So these are simulations for proteins, and this is real experimental data from the LCLS, where we've taken snapshots of iron oxide particles in solution in random orientations, more or less identical, and reconstructed an image of one of them, our typical particle. Okay, I'm done. This has been a huge international collaboration. I have to mention the people involved. Henry Chapman has been a tower of strength throughout. I've worked closely with Mike Berger at SLAC, and Janis Hoydu has led the single particle effort, which I haven't had time to talk about. So let me just say that there was another paper in addition to the nanocrystal paper, which we were peripherally involved with, in which Janis's group got, I guess you could say, the first X-ray diffraction pattern from one virus. And from that, they were able to reconstruct an image of the virus at about 300 angstrom resolution. So it's much worse resolution than cryo-EM, but it's a technique that, of course, will be developed as these X-fells become more powerful. James Holton and Bill Schlichting have also been enormously helpful and supportive. So just to summarize then, I've said that in the last 10 years we've seen lensless diffractive imaging and typography allows us to see inside mesoscopic structures. And I can tell you that the Department of Energy is very interested in mesoscopic as the next big thing after nano. So our X-rays are just the right tool for that length scale. We don't have to apologize for the resolution anymore with our X-ray diffractive imaging, because we're all going to be studying meso, not nano. Right. Using a TEM, convergent beam is now a highly quantitative method and can be used for bonding refinements. X-ray snapshots without damage at atomic resolution have been shown. I'm simplifying things a bit here in the interest of time. But short pulses, instead of freezing, this is the main point. Short pulses, instead of freezing, allows room temperature work. That's the key point. And hence we can study chemical dynamics. And I didn't mention that if you work out the dose that we deliver, it seems to be that if you deliver the dose sufficiently quickly, you can deliver 100 times more dose. You'd call this a reciprocity failure, I guess, in photometry, in radiometry. So crystallography has solved nanocrystals, and I showed you an example in vivo crystallization in bugs. And a good idea there, I think, is to study crystal growth itself. I mean, so we get 2D snapshots, right, of nanocrystals at various early stages of growth. Nucleation growth, screw dislocations, Frank, all that stuff applies. Can you see a way to use those to understand the growth of proteins at the early stage, as McPherson has taught us we should be doing? Now, it's a tough problem because you can't merge the data. You get 2D snapshots of different nanocrystals. Every crystal is different. But surely there's a way of looking at these 2D pictures and drawing some conclusions about the mechanism of protein crystal growth. I've described our new direct low-resolution phasing method. What's good about that is using the fringes between the Bragg spots. It's independent of the number of atoms. You don't need atomic resolution data as you would for direct methods, and you don't need chemical modifications to the sample as you would for MAD and SAD. So there's also the fast MAD work going on. I mentioned correlated fluctuations in snapshot sacks, which gives ab initio inversion. We get a picture of one particle using scattering from many in solution. And I haven't talked about fast electron diffraction, which is also a very active field competing with this. Those people would like to make a tabletop apparatus using femtosecond electron diffraction instead of having to spend 600 million on an X-ray laser. And the performance is not there yet, but maybe eventually. And finally, I mentioned the thing I'm most excited about, I think, is this toothpaste LCP and sponge phase jet, which should be very good for the people interested in GPCR, coupled protein receptors. So my conclusion then is that there's plenty of diffraction physics remaining to be done in all these areas of static, time-resolved, single particle, fast wax, and nanocrystal crystallography, and that our field is by no means mature. Thank you.